Hello and welcome to Lecture 16 for Introduction to Astronomy. This is Stellar Evolution Part 2. So previously we learned about the beginning stages of stars' lives, such as how they form and how they live on the main sequence by fusing hydrogen into helium in their cores. And then we touched upon the red giant stage and a little bit about how they sometimes group themselves into different clusters. But in today's lecture, we will learn about how the last stages of the star's lives go. So we will learn about the helium flash and the triple alpha process. We will learn about how planetary nebula are created and surround a dying star. We will learn what white dwarfs are and what the Chandrasekhar limit is and how that applies to white dwarfs. We will talk about neutron stars, which I'm a huge fan of because I did my master's thesis on neutron stars. Go neutron stars. And then we also will talk about type 2 supernova. And lastly, nucleosynthesis. How did all of the elements in the universe get forged? And how are they present in the numbers that we see today? We've been talking about stellar evolution for the past few lectures, and this applies to nearly all stars. Each start out as a nebula, and then they become a protostar, and then they become a main sequence, and then a giant or supergiant. But the nuclear exhaustion is mass dependent. So more massive stars will evolve way more quickly. And this creates a much wider range of possible behaviors due to how much mass they have and the potential that that gives for different types of fusions. And so for this course, we will only focus on the key stages in stellar evolution for single, that is isolated, massive stars, and how these evolutions of high mass stars differ from more common low mass stars like our sun. So first we're going to talk about the triple alpha process. So for stars that have masses close to our sun, that is less than or equal to 2 times the solar mass, once the helium core has been formed, they no longer have a source of energy except for gravitational contraction. The gravitational contraction in the core heats the star's temperature until the temperatures reach about 100 million Kelvin. And once those temperatures have been reached in the core, you can then have 3 helium atoms combine to form carbon. This is called the triple alpha process. So a helium atom is composed of 2 protons and 2 neutrons, and that was initially called an alpha particle by early scientists who were studying types of radiation. When very heavy elements like uranium decay, they often decay by spitting out a helium nucleus or an alpha particle. And so this is what we call the triple alpha process, when 3 helium nuclei fuse together. They all collide and form carbon. And so we can see that this actually happens by the first 2 combining into beryllium, and then that beryllium then combines with another free helium, and that forms our carbon. So once the triple alpha process begins, this gives a quick burst of fusion known as a helium flash. This releases a lot of energy, and this heats the helium core even more. This helium flash speeds up the rate of fusion, which creates a runaway generation of energy, which reignites the helium core. So this is going to be a much more brief stage of fusion than hydrogen into helium. This is not a main sequence process. After the helium flash, the giant star begins to find its balance again, so to speak. It needs to readjust for the release of energy from the triple alpha process. So this causes the surface temperature to increase and the overall luminosity to decrease, moving it to the lower left part of the HR diagram just below the red giant section. During this semi-stable phase, and I say semi-stable because it lasts only millions of years, or even less for even more massive stars, So during this stable phase, the inner core is primarily converting the helium into carbon. While as soon as all the helium has been used up, the core will then contract again. This subsequent contraction heats the surrounding layers to the helium fusion temperatures, and once again, it then moves to a different location on the HR diagram, known as the and becomes a second generation giant. This is because of this second contraction after the helium core has been converted into carbon. And then you have the outer layers then be able to do helium fusion. So unlike the previous giant sequence, this carbon eventually this new fusion stage of carbon oxygen will not actually rescue it, and the second giant generation stage will actually be very brief. It cannot do that trick of contracting again to further its lifespan. As stars get more massive in their later stages and they swell up to their giant sizes, as that radius grows, the escape velocity decreases. And so during these phases, the pressure and the pulsation and the helium flash all drive material and atoms away from the star, which causes a substantial loss of mass. This can be up to nearly 25% of the initial mass of the star, and all of that mass then goes into the surrounding space. Once all the nuclear energy has been exhausted, the core shrinks and heats up again, and it becomes even more compressed until the surface temperatures are as high as 100,000 Kelvin, and they produce very strong stellar winds and UV radiation. This heats and ionizes that surrounding gas into an H2 region and causes those gases to glow really brightly and fluoresce. This fluorescent glow that surrounds the dying giant stars are known as planetary nebula. Now, this doesn't have anything to do with planets inside the nebula. This is just named after the fact that they have a pretty close to spherical shape, and when early astronomers first found them in the sky, they were much larger in extent than the point-like stars, and so they looked kind of planetary. However, the astronomers could still tell that they were a little different, and so they got the nickname planetary nebula, and that's just sort of stuck. This loss of mass during the dying phases of the star is a quintessential part of that cosmic baryon cycle which we've talked about. However, the original material has undergone change, and there are a lot of new elements that are being released out into the interstellar medium. And so this provides the building blocks for the complex universe that we see now in our current day. All of these elements that are very heavy, like the iron in our blood, or any gold or platinum in our jewelry, all came from very massive stars. So now let's talk about what happens when low mass stars have completely run out of nuclear fuel and are going to die, so to speak. So if the initial mass is less than or equal to 2 times the mass of our sun, that is the threshold which we say for low mass. Medium mass stars are about 2 to 5 times the solar mass, and then massive stars are anything greater than 5 times the solar mass. So, if you are a low mass star, after you have a carbon oxygen core is done compressing, no more fusion can occur, and you are now in an energy crisis. How do you stop the inward contraction of gravity if you don't have any outward pressure from nuclear fusion? And so, without an energy source to provide that outward pressure, gravity compresses the star until pressures are massive, about 10 to the 6 bar. And so, at this extreme pressure, matter behaves in a different way, and the star has to go to a new type of equilibrium. At this extremely high density, this gravity attempts to shrink the star even more than is physically possible. And so the electrons actually resist this pressure because electrons don't want to be in the same energy state. This is known as Pauli's exclusion principle and is due to the fact that electrons are known as fermions. That is, they are a type of particle that has different spin statistics. But that's getting into very uh, deep quantum physics. What you need to know is that the electrons don't want to be in the same energy state, and so they provide a pressure, a resistance due to the Pauli exclusion principle. And so that stops low mass stars from contracting even further. So throughout the fusion in the star, Pauli's exclusion principle was easy to maintain, but after the star collapses, the electrons exert that pressure because they don't want to be in the same place and moving in the same way. Physicists call that a degenerate gas, which does not require heat to maintain pressure. So now we have what we call a white dwarf. These are the dying stable stars that are composed of that electron degenerate gas that will not contract any further. And they will exist in this state virtually forever. Their only energy source is from that heat that they still have stored due to being a hot star in the past. And they will gradually radiate this heat away, and after billions, or actually trillions of years, they will not be emitting any more light. They will be what is known as a black dwarf. This is a stellar corpse that is no longer emitting really any light and is composed mostly of carbon, oxygen, and some neon from final nuclear reactions it experienced, and it is now, when it is a black dwarf, it is essentially a cold diamond. However, there are no black dwarfs yet because the time that it would take to radiate all that energy away is much longer than the current age of the universe. So this is just a hypothetical final stage. Right now, all white dwarfs are still white dwarfs. They have not radiated their energy away to become black dwarfs yet. So now that we know that white dwarfs are held up by that electron degeneracy pressure, we can talk about the Chandrasekhar limit. So Dr. Chandrasekhar was studying white dwarfs, and he postulated that there was going to be a final diameter that these white dwarfs could have based on how much they could shrink before the electrons stop it from shrinking any further. He found that the maximum mass that a white dwarf can reach is 1.4 solar masses before the radius would be zero. And so a radius of zero is not really physically possible, except maybe as a black hole. And so, but that wasn't known at the time. And so this provided a loose limit, a rough limit for the mass of a white dwarf star. And so degenerate electrons cannot stop the gravitational collapse of a star if there is more final mass than 1.4 solar masses. And so this suggests that stars that have a final mass greater than 1.4 solar masses will have different ends than being a white dwarf. Fusion in massive stars is very different than fusion in lower mass stars. So we can see in this diagram on the lower left, this is what we call onion fusion. So, because it's got so many layers, just like ogres. So this diagram shows us that at different radii in this massive star, it has the necessary densities and temperatures for different types of fusion. So very massive stars that are 5 times the mass of our sun or greater, will have lots of different types of fusion in their layers. And when massive stars reach the end of their life cycle, they have violent, explosive finales. So after the helium in the core is exhausted, carbon can then be fused into oxygen, neon, and magnesium. And after each one of these fusion stages is done and the fuel of that stage is exhausted, the core contracts again until it can fuse even heavier nuclei. This goes all the way up the periodic table through silicon, sulfur, calcium, and argon, and ends at iron. After iron is produced in the core of massive stars, it's game over. It is no longer possible to generate energy by fusing two iron nuclei together. In fact, it takes energy away to fuse iron nuclei together. And so the star is doomed after it reaches that stage where the core has become completely iron. So that is that final stage. And once it has reached iron in the core, it is a very rapid death. Sometimes this can be only months to days. And when iron is formed, the core is briefly supported by those degenerate electrons, but this is not going to last. And so as the successive layers of the massive star halt their fusion, they eventually fall into the core. And once the core reaches the density greater than the Chandrasekhar limit, where electrons can no longer support the mass of the star, sometimes these electrons are then squeezed into the protons and form neutrons, which also then form neutrinos to balance out the numbers. And sometimes, I say sometimes that happens. It actually will always happen, but sometimes that creation of neutrons is enough to halt the process of collapse. There is a corresponding neutron degeneracy pressure. So if the star is very massive, but not massive enough to become a black hole, it will become a neutron star. So in this type of reaction where we have a electron and a proton combined, this gives us a neutron and a neutrino. And so now many of the electrons are gone, and our star is composed primarily of neutrons. And this supports the force of gravity and stops the collapsing thing uh, from being collapsed further. So the neutrons are squeezed together and gives us a neutron degeneracy force that is much greater than the electron degeneracy, since neutrons also don't want to be in the same place and moving in the same way. This huge ball of neutrons is called a neutron star. But unlike white dwarfs, there is not currently known what the exact number for the maximum mass of a neutron star is. That's one of the things that I studied for my master's thesis, and surprise, surprise, I didn't solve it. But I learned a lot along the way and helped give my advisors some interesting insight. But anyways, we think that stable neutron stars must be less than 3 times the solar mass before neutron degeneracy is overwhelmed. And at that point, that is when the collapsing star becomes a black hole. Neutron degeneracy pressure cannot stop the collapse, and then it becomes this mysterious, really fascinating object that we call the black hole. So when neutron stars form, they happen during type 2 supernova. The neutron core is safe, but those outer layers are going to rebound during their collapse inwards and create a huge explosion. And the collapse of the degenerate electrons into degenerate neutrons is very rapid and can happen in less than a second. And so the core, which was once the size of the Earth, then collapses down into 20 kilometers. This means that matter is falling at nearly 1/4 the speed of light. And then when it hits the core and the neutron degeneracy pressure resists further collapse, those outer layers rebound outwards in a huge shockwave known as type 2 supernova. The energy that is created during the fusion of electrons with the protons into neutrons, that releases lots of neutrinos, and those neutrinos carry a lot of energy. Even though neutrinos interact with matter very rarely, the fact that there is so many of them and there's so much matter around the star still, it actually creates a huge energy output, 4 or 10 to the 46 watts of power, which is greater than all of the output at a single time of all of the stars in a galaxy. So this when this happens, this creates a massive explosion called a type 2 supernova. So we've talked about how these fusion cycles create different elements, and in the massive stars, they have all of these layers, and so this creates lots of variety in elements. And so now we can talk about nucleosynthesis, how all of this primordial matter became stars and then these heavier elements. So all stars take hydrogen to form helium, carbon, and oxygen, and then the more massive stars create these heavier elements, and then when they explode, eject it out into space. Massive stars' temperatures allow for those complex fusion cycles after carbon and oxygen. And if the mass is greater than 8 times that of our sun, we will get a lot of oxygen compressing into neon and magnesium, and then silicon, sulfur, calcium, argon, and iron. And these are all elements that we can find in our body and are necessary for life. Iron is the most stable atomic nuclei, and it is the stopping point for fusion in massive stars. But the universe is filled with far more complex nuclei than just iron. And so when type 2 supernova occur, this actually creates even heavier elements than iron because you have all of those neutrons and protons and whatnot. This creates the conditions and densities necessary to create some of these heavier elements. They are smacked together during that core collapse phase and the outer rebound. And so these heavier elements created are then recycled back into space. And so this process of fusion and creating nuclei up to iron is known as nucleosynthesis. And physicists can determine the abundance of atoms throughout the universe based on this nucleosynthesis process. So as I said, the more complex nuclei that are heavier than iron are created during these supernova events because of the extreme energies released in supernova. And these processes are the catalyst for the cosmic baryon cycle and explain why the building blocks of life coalesce to form us. These heavy elements were created in the cores of stars and then recycled into new generations of stars that became us. So, astronomy is our best scientific attempt at understanding our universe, and it finds conclusively that all of the material that makes up every atom in your body and the world around you was forged in the heat of stars and star death. And so Carl Sagan very famously said, the cosmos is within us. We are made of star stuff. We are a way in which the universe knows itself. It's a very powerful quote, and it really speaks to the just wonder that astronomy attempts to capture through the scientific process. It is a beautiful thing, and it is I love astronomy, and I hope that you are seeing how the science of astronomy connects all of us and everything in the universe. This concludes lecture 16 and part 2 of stellar evolution.